Okay, so as I was saying, you can't use any numbers for k other than an odd integer other than 1 or 13. If you were to use an even integer or use 13, some of the letters would start to overlap as you would multiply them and then try to mod them down to mod 26. And we'll come back to that, and you'll be like, oh yeah, but we need some more experience with modding probably first. Okay, so again, first thing you do is convert. I have a lot of these now, these more complicated ones written out in step numbers for you. Convert your plain text number in message into numbers. Then for each number, multiply the number by k, mod it down or reduce it mod 26, and convert that back to a letter using this chart. This chart I'll print for you on quizzes and tests. You don't have to memorize it or write it down yourself because that's kind of a waste of time. So we're talking about the letter H. Just do one letter. So if the letter was H, the letter H goes with 7. Notice if you multiply 7 I chose a value for k. Actually, one of these steps here should be choose a number k. I didn't put that as a step. Usually that's given, actually. Anyway, so here are the numbers. The number k is 11. So my h is 7. I turn that into 77. 77 mod 26 turns into 25, which tells me the h turns into a z when I try to encode it. So that's how that works. But you're going, oh my gosh, really? Will z ever get me back to h? Okay, here's how you undo, because all of these ciphers come this way. You have to figure out how to encrypt and how to decrypt. If you know the rules of the cipher, you should be able to figure that out. Or, it's sort of hackable if you know how someone encrypted it. So, yeah, so on quizzes and tests, I'll give you a scrambled message, and we'll do that here too. And it says, okay, this was done with a decimation cipher where k was blah. I'll give you the value of k. You figure out how to undo it and get back to the regular original message. So anyway, to undo a k of 11, turns out that here's the list of possible k's you can use. So here's all the odd numbers that are not 13 or 1. Each one of these comes with a decryption key, kind of. And now, how did they get these decryption keys? How do we know that if I use 11 to encrypt, how do I know that 19 is going to decrypt? Well, here's why. Notice if we took, 11 times 19. If you take 11 times 19 and you mod that thing, 26, watch what happens. It turns into 1. So 11 times 19 is 1 more than a multiple of 26. And it turns out that's going to work with all of these rows. 3 times 9 mod 26, well, that's 27, right? 3 times 9 mod 26 is 1. Same thing for 9 times 3. Notice that always happens. So if I have 3 for encoding and 9 for decoding, it's going to work sort of commutatively. 7 and 15, down here I find 15 and 7, because that product turns out to be 1 more than a multiple of 26. And what's kind of cool is every odd number other than 13 up to 25 has a partner, kind of, that will always do that. And that will work for not only 26, but lots of things. We're going to do that kind of in general by the time we get to the end of this unit. And we study more modding things. And so I say here, welcome to number theory. Number theory is all this kind of stuff, and it's really fun. I'm talking about primes and remainders and kind of like generalizing theories about that. It's really, really kind of fun. You can take entire courses in number theory. This is just the tip of the iceberg, but it's super cool. Okay, so yeah, also by the end of the unit, you'll get better at finding these inverses. Here's the table for the 26, basically, for the world where you're using things mod 26 or the Z26 world. And that's really common. We're going to use that because of the alphabet being 26 letters and that kind of thing. But we will talk about inverses and mods in general a little bit later. Okay, so to decrypt, since I was told, so you're not completely hacking this. Like someone sent you a message and said, oh yeah, by the way, I encrypted this with the decimation cipher where I used k equals 11. And they tell you that secret information. And if you knew that, and I would tell you that on the test, you'd know you were sent a z, and you go, okay, yeah, z is 25 from the chart. I'm going to take 25 times the decryption key, so 25 times 19 gives me 475, and yes, 475 mod 26 comes back to 7, and 7 tells me where I came from. So isn't that just the best thing ever? Okay, great. So I took this from, I do these little messages that I get from, pop culture or, something that I think you guys ought to just know about, like, culturally. This comes from a song lyric. You should probably know what that came from. We'll talk about that in class. You can impress me with your knowledge of things I'm interested in. All right, so anyway, what happens here? So the first thing we do is we convert all this stuff into numbers. So R turns into, just so we have numbers to start with, R turns into 17, U turns into 20, n turns into 13, etc. I don't want to make you watch me do all this. So that's just all of those characters turned into numbers. Notice I'm ignoring the spaces. I'm not using x's as my spaces, and I don't have a number for a space, and that's how this one works. And then, oh sorry, I didn't finish it. I thought it was on the next page. It's on this page. All right, let me keep. All right, so the next thing I do is I take each one of those numbers and I multiply them by the value of k. And here I was told that the value of k is 5. So that 17 is going to turn into 85. I can use my calculator for this. The 20 is going to turn into 100. 13 is going to turn into 65, etc. So I should write what I'm doing here. So simply I just turned them all into numbers when I got here. And then here I took each one of those and I just multiplied them by k times 5 because of that. And then the next thing I'm supposed to do is mod these, because now these aren't letters anymore, right? Now these are, well, most of them, they're numbers that are beyond this, so I need to mod these all down 26, and then we'll get a new string of numbers. So 85 mod 26, let's go to the calculator. Mod 85, comma 26, that's going to be 7. All right, where am I going back here? So that's going to turn out to be 7, and then I'll do that with all the rest of them. 100, I can do that right now. For the next one, 100 mod 26 is going to turn out to be 22, etc. And it turns into this once I mod them all 26. And once you start doing that, you'll start to see patterns. You'll start to think it'll go faster than typing them all in individually. And then I can figure out the plain text message from that. The ciphertext message from that, if I convert these now, looking back into the chart, into letters. So, and notice I ignored spaces. So I could put spaces back in here to help the reader if I wanted to. H, W, 13 is N. I could put a space because I know there's again, I'm still in the encrypting phase, so I know there's a space there, so I might want to put a space. You might see a space in the stuff in the answer keys or in the tests and things. 17 is R, I did that right. 18 is S, back to R, etc. Okay, and there's our encrypted message. You may have noticed that I made a couple mistakes here the very first time. Some of these were 85s, I fixed them, and I fixed a spacing thing here just now. The miracle of editing. Okay, there's the encrypted message from this original thing. Now, if I want to try to, if I was going to try to decrypt it, sorry, it says and decrypt. If I was going to try to decrypt that, I keep trying to turn the page. I have to take each one of these. If I received this message as the receiver, I would decrypt this, kind of trying to go backwards through all these steps. So first thing I would do is I would take this and convert it to numbers. That's not hard. Then to get from these back to these numbers, because that's really the trick here, right, is to figure out how to get from this 7 to the 17. I would multiply all these numbers by the inverse of the 5. Remember, the person sending the message would send me some other way to tell me that it's encrypted with a 5. The decryptor for 5 is 21, so I would take 7 times 21 mod 26 to figure out what the next thing is. So first of all, let's multiply everything by 21. All right, I realized I was going to run out of room, so I took this encrypted message that we ended up with down here, made some blank space for me. So we've been sent, imagine you're the decryptor now, you've been sent this message, and you know it was encrypted with k equals 5, so that's helpful. We convert that to letters, then we take each one of those letters that have been turned into numbers, and we multiply those by 21, because I know 21 is the sort of the decryption key that was called J on the other page. I know that J equals 21. So I multiply each one of those times 21, and then I mod 26 again to turn those into actual numbers from the letter chart. So 147 mod 26. I'm doing this again, so I'm still modding 26, so that turns into 17. And etc. I'll do the rest of them so you can check. And by a miracle, yeah, when I mod those 26, they should turn back into this list, which we saw before back here, and then converting that back into letters, I'll get back to the message I originally started with to encrypt, that was encrypted to me. Okay, yeah, I said we were going to talk about this, how to find inverses mod n. I made a little table here of all the numbers in Z7. So if I was going to find the inverse of all those mod 7, it's not that hard to actually just make a table and kind of guess and check your way through this, because there's not that many integers in this list, right? So these are all the integers that are possible in mod 7. Actually, I didn't use 0. 0 doesn't have an inverse because there's nothing I can multiply 0 by that's ever going to turn into 1 mod 7. multiply 0 by anything, it's going to turn to 0, and it's not going to have an inverse. But everything else has some kind of inverse. Probably not surprising that 1 is an inverse of itself. So, or 1 is already, 1 mod 7. So if I multiply it by 1, it stays that way. We already talked about the partner type relationship because the commutativity of multiplication. It also turns out, and this is a little more interesting, that n minus 1 times itself is always 1 in that mod universe. So in mod 7, 6 times 6, if you think about it, 6 times 6 is 36. And 36 mod 7, yep, that's 1 more than a multiple of 7. It's 1 more than 35. Then there's not that many left to check, and I probably won't give you a list much bigger than this. But just of the remaining elements here, from 2 to 5, each one of these has to have another one as a partner. So if you think about 2 and think about what other numbers it could possibly have that I could multiply these by to get a number that's 1 more than a multiple of 7. So we're talking about numbers like 8, 15, 22, right? Because I'm thinking 1 more than each multiple of 7. Turns out 2 times 4, of course, is 8. So 2 and 4 are partners, and 3 times 5 is 15 because they're 1 more than 14. We will get more. Oh, here's some practice right here. Let's make the table. Okay, and I want to start drawing your attention to the fact that we should call this Z11. And that's what's going to look like on the test. Okay, so I made a little list of numbers over here, and I made a little list of sort of potential dance partners over here, and I can just drag these around into place. We already talked about this, that the inverse of 1 is 1, because 1 times 1 is 1 in Z11. The other thing you can always know is 10 times 10 is going to be 1 more than a multiple of 11. Yeah, multiples of 11 go 11, 22, 33, up to 121. I guess we don't have to go that far. What's 10 times 10? 10 times 10 is 100, and yep, believe it or not, 99 is a multiple of 11. So 10 times 10 is 1 more than a multiple of 11. All right, think about 2. Which one of these numbers can I, because these are the ones that are left, what number can I multiply by 2 to get a number like 12? Oh, there we go, 12, I got it, 6. So 6 goes with 2, and 2 goes with 6. That's lovely. 3, can I multiply by 3? Can I multiply 3 by something to get a number that's 1 more than 11? 3 times, like 12? Oh yeah, sure, I can use 4. 3 times 4 is 12. And so 3 goes with 4, and 4 goes with 3. What about 5? Well, I can't get to 12. What's the next one? That's 1 more than a multiple of 11, so 23, that's no help. 33 plus 1 is 34. That's no help. 44 plus 1 is 45. There we go, 45. So 5 times 9 and 9 times 5. And guess what? I bet it's going to be 8 times 7 and 7 times 8. Whoops, what is that? 8 times 7 is 56. Yep, that's 1 more than 55. Isn't that just the coolest thing you've heard all day? I love that. Okay. All right, so linear cipher is really just a combination of the last two things we just learned. So Caesar was about adding, decimation was about multiplying. So now we have both those things at the same time. There'll be a key where you have a multiplier and an adder, and of course we're just going to mod these all down to 26 so that they fit into our alphabet. Okay, so encrypt and decrypt the following message using, and I made it really short, and I made the word virus because it's relevant and current and you're thinking about it right now. Okay, so let's change this into numbers. Just realized I have very little time. I'm going to try to pause and do this by editing in less than a minute and a half. Okay, so that's as letters. Then by order of operations, of course, we multiply by 15 first. There we go, and now we're going to add 4. And then just as before, we're going to mod all these 26 to get back into the alphabet. And I realized a little oops there. I had a 270 before, 274. Mod that 26 and change that back to letter. And there's our encrypted word. All right, let's try to decrypt it. Now in decrypting, just be careful of order of operations. You want to make sure you undo this the correct way. Let's try it. So you've received this encrypted message. You know it was done using the 15x plus 4. And so the first thing you do, of course, is convert it into numbers. And there they are. Now, you know, the last thing that was done in the 15x plus 4 was the plus 4. So the next thing we're going to want to do is minus 4. Now, realize when you minus 4, say you had a number here that was less than 4, and you subtract 4, you're going to go negative. You could actually leave it as a negative number, and it will work. Or if a negative number bothers you, notice like if you got like a negative 2, you can go negative 2 mod 26, and you're going to turn it into 24. That's okay, because remember, we can loop this around the alphabet. Okay, now we have to undecimate this thing, and this was decimation times 15. And way back on this page, we find out that the inverse, to undo the 15, the inverse we need to use is 7. Then, of course, lastly, mod 26 and change back to letters. And wow, I almost have 15 seconds left. Okay, I'll see you in class. Thanks. Woohoo!